Hello and welcome this afternoon to the Digital RE Days. We are coming close to the end of our event, but it's not over yet. So let's have a look to our next presentation. My name is Doreen Schäfer and I will moderate this session. Next to me is Aldo de Michiel. Hello.
Perfect.
And he's going to present you transformer design considerations and Midcom capabilities. I'm looking forward to this one. So the stage is yours.
Thank you.
Enjoy it.
See you later.
See you later.
So, good afternoon and also a warm welcome from myself. My name is Aldo de Michiel and I'm a design engineer in World Electronics Midcom here in Europe. In Midcom, we are specialized in custom magnetics and transformers. And in this presentation, we will go through some design consideration, what parameters affect a transformer design. And at the end, we will have a look at our capabilities. We will see together some packages that are preferred for us. And together we will see if there is a best one or one that can choose and suit your application. So let's start with this presentation, starting from the agenda. So we will see what do we need to start a custom design. We will do a quick example of a course selection, how the safety affects the design. We will see a showcase of our manufacturing capabilities. We will make a quick package comparison at the end. But first of all, let's see together how a typical transformer looks like. So here I presented a blueprint. Oh no, maybe this is the wrong one, because what we do is a different type of transformer, but maybe we will introduce this capability in the future. So now, jokes apart, let's see for real what do we need to build a transformer. So building a transformer is relatively easy, and normally we start from the bobbin, which is a plastic component that used to wind our windings on it. It provides insulation and mechanical support. Then, of course, we need the wires, which in general they are made out of isolated copper, and the diameter is defined by the current, and the isolation can depend by the safety requirements. Then, of course, we need the core. We can see that the cores, they can come from different shapes. They are made out of ferromagnetic materials, and its purpose is to improve the efficiency of energy transfer between the primary and the secondary circuit. And then to conclude our transformer, we need other components such as clip, adhesive, varnish, and tapes. Not only they provide the mechanical stability during the assembly, but also when the component is finished. So for us to start a custom design, it's important to collect all the information at the beginning. Once you have shared all the information with us, you don't have to worry about the transformer design. We will do it for you. But for us, it's important, as I said, to collect it in one document, and what we use is an inquiry form. So as an example, we need information such as company and project. So we need to know your contacts and commercial details, so we can get in touch with you. Then, of course, we are designing a power transformer, so we need to know the input, output, ICs, topology, and other important electrical information. Then, of course, we need the safety requirements. So this is defined by your application. And this is a very important information to know as soon as possible, and we will see later why. And then we need to know if you have any mechanical restrictions in your PCB, for example, height, length, and width, and if you have any preferred pin shape, for example. And you can see the other details more in the deep in the inquiry form. I will attach the link to the presentation, and for any other question, you can get in touch with us. Before going through the design, we need to make some initial considerations that the perfect solution does not exist. It never exists, especially when we do a custom solution. Every project, every part is different, and together we need to see where we need to put our focus. And if your priority is, for example, cost, safety, dimension, performance, CMC. So we work in such a way to do a design together with you to keep like an active communication, and it's important to know this information as soon as possible in the design. So the package choice is very important when designing a part, and we can see quickly what are the criteria that will impact this decision. So for example, what is the shape of the transformer? If you need a vertical or a horizontal part, what is the pin style you're looking for, a SMD or a through hole, because then at the end will determine different footprints. If cost is your priority, we have to keep in mind to keep the part as simple as possible, and therefore in our production we can use automating winding and assemblies. At the end, safety, we will see later, is a hot topic for us. If we need to respect certain standard and distances, also this can create some restrictions. So share it with us as early as possible. And then if you need to achieve some EMI compatibility in your parts, we have some core shapes that offer a better shielding solution than others. Of course, the power is very important to know, because the power at the end will determine the package and the overall dimensions of the part. And it's, of course, is probably the most important information we need to know. And then the pick and place. So if how your part will be assembled and put on the PCB is very important, because we have parts that have some excellent flat surface on the top, or clips and caps can add it in a second moment. But to start a design, let's start from the core, which is for us in general the design starting point. I will not go into the deep of electromagnetism. I showed that most of you already saw that laws enough in university, but as a basic rule, the core is selected depending on the power requirement. And in general, the maximum power of the core is directly proportional to the cross-sectional area. So it means that the bigger the cross-sectional area, the more flux can be present in the part without having it saturated. But this is also proportional to the switching frequency, because the higher the switching frequency, the less magnetic flux is needed to transmit the power. So now let's do a quick core selection, and I prepared an example of a low power versus a high power core. The topology is the same, is a DC-DC flyback that works at 100 kHz. And what we are comparing is an EP7 versus an ETD39 core. So let's start from the EP7, and I put side by side the power versus frequency curves. So we can see here the dashed line, which is the DC-DC flyback curve for the EP7. So we set the switching frequency at 100 kHz, and this will result in a maximum power achievable of 3 watts. This is the maximum power we can achieve with this core, with this topology at this switching frequency. But now let's check a slightly bigger package, like the ETD39. So let's find the same core, which is higher here. The frequency is the same at 100 kHz, and in this case we will obtain a power of 400 watts. So it's almost or more than 100 times similar, 100 times bigger. But why? Because if we put the two transformers side by side, we can see that the size is completely different. We have on one side a part with 6 pins and an SMD, while on the other we have one of the bigger packages in our portfolio. So this is clear that the power is an important parameter to consider in the beginning of the design stage. I said before that safety for us is a very hot topic for us engineers, because it will add a lot of restrictions in terms of mechanics, in terms of materials, and it's very important to know this information from the beginning. But first of all, let's see together what are safety standards. So safety standards, per definition, are mechanical and electrical precautions to protect the user in case of fires, electrical shock, and injuries. There are many that we use every day, but I summarized the best sellers we use just to give you some examples. So let's start from the IEC 62368, which is a safety standard for audio, video, and information technology equipment. I wrote it because it's important to know that it replaced the IEC 60950. Then I put this one in bold, which is the IEC 61558-1. Most of you probably know that this is the general safety standard used in power transformer and general power supplies. And most of our safety standards are somehow related to this. Then another very common one is the 61010-1, which is a safety standard for laboratory equipment and measurement control. And to conclude this list, we have a safety standard for medical equipment, which is the 60601-1. So I would like to make a consideration that we can calculate all the creepage, clearance distances, the material restriction, but we cannot select the safety standard for you. This has to be decided by your side, depending on the end application of your part. But if at the end you need an official safety certification, we work with the main safety agency in Europe and in the US, and we have good contacts, and we can help you and provide you support during this certification stage. So what kind of information do we need from you to calculate the creepage and clearance distances? I will make like a short list, and then we can see this information later a bit more in the deep. So we need to know your insulation grade, the overvoltage category of the application, the pollution degree, if the altitude of the end application is higher than 2000 meters, and then the max peak working voltages. And all this information are summarized here in our Würth Electronics Midcom inquiry form. And be careful, because if the form is not filled out well, we will get in touch with you, because without this information, we cannot start a design for safety. So let's see these details a bit more in the deep. Let's start from the insulation grade. And the easiest one to achieve is called functional insulation. So there is a grade that only guarantees the proper functioning of the equipment. I put between brackets 0 layers, and this does not mean that we're using bare copper, otherwise we will have a shortcut, but the wire is only insulated through enamel, so this does not take part of any insulation grade. Then, increasing a bit the level of safety, we have the most simple one, which is basic insulation. So we have only one layer of safety to achieve a certain protection against an electrical shock. Then this grade is not that common for us, but with supplementary insulation, we have 2 layers of insulation. And then let's see the most common one, but also the most difficult one that we have to achieve, which is the reinforced isolation. So to achieve this one, we need 3 layers of isolation, and a common component that we use to achieve this grade is a triple insulated wire. We can see here, and I wrote it as an example to explain you quickly what we are talking about. So we can see in orange, we have the conductor, which is a bare wire, and we have the first, the second, and the third layer of isolation. So you can see that we are talking about 3 layers. And to conclude, in general, the higher the insulation grade, the lower is the space available for the windings, because around this copper, we need to add the number of layers needed, and in this case, we are sacrificing pressure space that we will need in the winding area. Okay, now we are talking about the overvoltage category, and the short story is related to voltage spikes and voltage transients. And to explain this concept, I represented a schematic here of a house where we can see the category 1, 2, 3, and 4. So increasing the overvoltage category, it means that we have greater chances of voltage spikes and transients, because we are moving closer and closer to a grid, and there are less stages of conversion and stability, and therefore also the safety needs to be adapted to this. So just some examples. In overvoltage category 1, we are dealing, for example, with USB equipment plugged to your cable. So we have a low voltage, we have a lot of stages of rectification before, and then the chances of voltage spikes are very low. Increasing a bit the overvoltage category, we have, for example, power tool, household appliances, so something connected, pluggable or permanently connected to the domestic grid. In overvoltage category 3, for example, we have the socket outlets connected to the building wiring. And then the most strict one, and we don't do many designs for this overvoltage category, are, for example, utility grade transformers or anything directly connected to the utility side. The takeaways of overvoltage category is that the higher the overvoltage category, the higher distance we need between primary and secondary. And this means that electrically we will have a worse coupling, because there will be more distance between the primary and secondary, and we need a bigger transformer. Now we are seeing the pollution degree, which is another important parameter to take into account when designing for safety. And in pollution, there are 3 main categories, and they start from the pollution degree 1. So in this case, we don't have the transformer is placed in an environment where there is no pollution that can affect the insulation. And an example can be a potted part or completely encapsulated. Then in overvoltage category 2, the transformer is in an environment where there is pollution but is not conductive. So for example, a typical office where there is some dust, there is some air, but nothing extreme. And then in pollution degree 3, we are talking about an environment when there is conductive pollution that can influence the isolation. So for example, a harsh industrial environment. And while increasing the pollution degree, it means also that the safety distance need to be increased, because these contaminants can create some conductive path, and there is a higher risk of arcing and then dielectric discharges. Let's see together some design techniques to meet safety. And I just summarize here some 3 quick examples. So in our first case, we can see that safety was achieved through the margin tape, which is the rubber tape placed in yellow between the windings and the pins. This tape is, let's say, bad for performances because it reduces the space available for the windings, but it is a compact solution because it will not affect the outside dimension of the parts. The second solution we can see is using extended rail bobbins, where I put here an example of an horizontal one and a vertical. In this case, the manufacturing of the part is easier because we don't have to add any extra component in the part, but unfortunately the part is bigger. There is always a trade-off. And then the third solution that we should try to avoid as much as possible is the use of fly leads. I'm saying avoid as much as possible because the wires are not terminated on the bobbin, and this will make the production from our side, but also the assembly on a PCB a bit more complex. But in this solution, long distances are achievable, so if I have any EMI experts live, you also know that this is bad because this can create unpleasant antennas. And if you're curious about designing for manufacturing, because at the end safety also affects how we build the part in our production, you can check another webinar clicking by the link here in the hyperlink in blue. So to summarize, I put a table to compare the safety, efficiency, manufacturing, and cost with a part with functional and so with no safety and safety. We can see that with no safety, the size, efficiency, and the other parameters are better. So it means that we have a smaller part, more efficient, easier to do, and also cheaper. But unfortunately, safety is not achieved. So please check this information more in the deep and tell it with us because it will influence a lot the design. And if you have any doubts and if you have any questions, we have another interesting webinar to how the safety affects your transformer design, still available in YouTube. But now we talked about a lot of design parameters, but let's see together some packages. So before looking at our capabilities and some custom designs, let's start by defining and mentioning why the packages are named in this way. What we're seeing is a EE25137, which is a pretty standard core. The name EE comes from the fact that we have two E cores facing one against each other. And 25137 is clear to say that they come from the mechanical dimension of the parts. But now, to not make you fall asleep in this afternoon and to engage you a little, we prepared a little quiz. We would like to see how many packages do you know, and if you have a favorite one. I have one personally, and I will share you later at the end of the presentation before the question. So you have enough time to think about it, and see you later in some minutes. So I prepare now a couple of examples of what the packages types for us in Midcom, and these are packages that are standard, so they're available, they're off the shelves, and they don't need any customization. So let's start again from the EE package style. The name comes from the fact that there are two E cores facing together. Remaining on the same power level, we can see here an EFD package style, which stands for economic flat designs. So I kind of agree that is a flat, which is because it's a very low profile part, but economic, really, I'm not sure about it. You will tell me more later what you think about. And then talking about low power, we can see here a ER package style because the core is a mix between an E and a round core. This is one of our best sellers, and this is also a very small package, which is a EP package because it's a mix between an E and a pot core. What we can see here is one of the biggest packages in our portfolio, and is a ETD package style, which stands for Economic Transformer Design. And now, in the same power range, we are seeing a PQ package. This package is very common in inductors and PFC, and probably that's why it was named after power and quality. And then one last package that remains in the same family is the RM package, which is called like this because it's a rectangular module. And it is one of the best packages we have in terms of a ratio between volume and power density. And I have to thank my friend and colleague Alfonso to provide this information because I think he spent a lot of time researching the origin of these names. So thank you, it's very good to know, and credits to you, Alfonso. And if you are interested to touch with hands and to see more packages. Anytime you come to any fairs or events, or some sales colleagues come to visit you, you can have a look on our red demonstrator boards, because we have more and more samples there. And if you like to study some PDFs, I also attach the catalog of our custom capability, where you can see more standard packages we're offering. But now let's go to some, let's see the packages we saw before a bit more in the deep. So I prepared some pack slide, let's say, and to not bother you, I will not go through any details. I will just mention some advantages or disadvantages on every package. But the presentation will be available, so you can check out the rest of details in your free time or when the boss is not looking at you. So let's talk first about the EP package. So this is one of the smallest packages we have, and the shape makes it good for many applications such as DGT, GDT, inductors, and push-pull. This part has a very good balance between a small footprint and a low profile. And thanks to its flat surface on top of the core, it makes it very good as a pick-and-place solution. Unfortunately, the winding area is a bit small, so at the end we cannot take out that much power from them. Still remaining in the same power level, so still in the low power, we can see the ER package. Of course, the biggest advantage is that it has a very low profile and is excellent for pick and place because it has a very flat surface on top. But unfortunately, it has a very small winding area, so it's not that easy to automate, and also the termination is a bit difficult, but there are always trade-offs. And then increasing a bit the power size, we can see a RM package. So this package has a very small footprint and a low profile, and is very used in inductors thanks to its big cross-sectional area here. It has a good power density, but unfortunately the pin shape and the geometry of the part does not make the automation of this package so easy. Now we can see again IE package. We are now in the mid-range of power. The shape makes very good for a small footprint and a low profile. And we have many products in our production. Therefore, we have many automated lines we can use in case of some high volume parts. Unfortunately, the power density is a bit average, and without adding a cap, is not suitable for pick and place. Now we are finally seeing my favorite package that I announced you before. This package is called EFD, and is my favorite package because it can come with a very shiny metal clip on the top that makes it very metal and is very elegant from my perspective. The shape, so the shape of this part is its biggest advantages because it is a very low profile and is excellent when adding a clip on top as a pick and place. But unfortunately, the size of the part is very low, the height is very low, and therefore so it has a very limited winding volume. And now finally, I present here one of the biggest packages we have in our portfolio, which is the ETD. And this package, thanks to its size and number of pins, make it good for many applications, such as half bridges, LLCs, push-pull, you name it. Unfortunately, due to its big size, it's only available in through-hole. Therefore, the pick and place is not available with this one. So to summarize, I present here a table with all the strong points of its packages. And you can see by yourself that the perfect package does not exist. We are talking about custom solutions, and the package needs to be defined and optimized depending on the application. So we are here. We have a big team in Europe, in US, in China, and we are here to help you choosing the best package for you. You don't have to spend hours in catalog and doing the design by yourself. Just get in touch with us and we can start the design. And if in the previous slide I did not convince you, or you did not find any package you like, we can also go custom. So I present here some examples of the parts we developed. So for example, this is an EFD10 with a 2-section bobbin and extended rails and designed for low profile. Now we have an EP7, so we modified the bobbin to achieve high creepage, and we reinforced it to also obtain a very high level of automation in our factory. And then another EFD10, here there was a requirement of a solid insulation between primary and secondary, so we added a center flange and a plastic barrier between the core and the windings. These are just some examples. In Midcom we have the capacity and knowledge to customize every component of the transformer, such as the core, the bobbin, the tape, you name it. And if you have any special requirement, just make your wish, because we can make it happen. So from my side, this was my last slide, but Bumblebee and I are ready to see the poll result and to reply to your question if there are any. Thank you for your attention.
Perfect. Thank you very much, Aldo. I hope everyone can hear me again. Perfect, it's working. Thank you for your presentation. I'm going to share the handout quickly to all of you, so everyone should be able to see the handout now, and you can download Aldo's presentation. So now let's have a look at the survey from you earlier. These are the answers. The question was, how many packages do you know? Ah, it's a good one.
Yeah.
I mean, most of them know packages. That's clearly good.
But I'm happy that there were 9 people that did not know any packages. So now we can go through the presentation and I can challenge you again for a small quiz. No, but I'm glad, yes. I think it was.
Now they are scared that you'll contact them.
Yes, yes.
No, but it's nice to see. A lot of you already know the packages, and Aldo explained the benefits of them to you. Okay, all right. So if you are ready, we can go to the questions.
Yes.
We have a few of them, so I'm just going to sort them quickly, and we can start with the first one from Herbert. So I'm not sure I need a custom transformer for my project. What a good starting point can be.
Okay. That's a very good question. And if you're not sure if you need a custom transformer for your application, the best and easiest way you can do is to simply get in touch with us, because we may have already something standard available without going to a custom design. And then if we don't find anything that satisfies your need, we can also consider a custom solution.
Perfect. Thank you very much. It's good to know. We have a lot of questions regarding the packages in the design. So I'm going to switch to that one from Marian. Are these inquiry forms for custom transformer design available on your website?
Yeah, the answer is yes. So I pasted on a hyperlink here in the presentation, which will send you to our online inquiry form page.
Perfect. Thank you very much. So that was easy to answer. So let's see the next one. I skipped from Samuel. What about the current during the core selection?
Yes, so you're right. The current is another important parameter to take into account, which is related at the end to power. But I did not go that much into deep, because otherwise we'll talk about magnetism for hours. But you're right, and there are some interesting tools you can use online, and you will see that also is taking part into the equations.
Yes, and if you have some follow-up question to that one, you can still contact us and we will forward the email to Aldo.
Yeah.
And he can answer it. Perfect. So let's see what's next. Mohammed has a question for us. Do you also do a customized planar transformer?
The answer is depends, and the best answer is just you send us the request and we can check it together, because the planar board is a bright one, so I cannot give you like a clear answer at the moment.
All right, thank you anyways. So let's have a look and hopefully we are able to help. So here's the next one from Maximilian. What's a typical MOQ for custom round transformers?
That's a good question, and I don't think we have a clear answer for that, because that will depend by the project information and also the price expectations you have. Simply send us the request and we will reply within 24 hours to evaluate the project.
That's super fast.
Yes, more than you expect. Yeah.
Are you also work on weekends?
Yeah.
Oh,
Maybe.
That's customer service. So let's check out the next question from Nadia. Do you design also encapsulated transformers?
It will be a future capabilities. We are working on it.
Perfect. So it's coming up in the future. Okay, Alex also has a question for us. Can you give us some outlook on new developments that would plans in transformers? So like a sneak peek you can give? Or not yet?
I don't think it's better you to follow our social networks and we will keep you updated there. It's
Okay.
a very general question.
Yeah, so let's see what the future brings. Okay, and we have another question from Herbert. What is the power range of your transformers?
That's a good question. So we call standard capabilities transformer that can go in the range between 1 and 1 or 2 kilowatts. But recently we added in our team a high power team that can take requests higher than 2.5 kilowatts.
Wow, thank you very much for the information. Something new. Okay, as I can see, we have one more question left from Dimitri. Is EPQ equal EP?
I don't have this on top of my head, but I believe that if the name is different, there is also probably a different there. But I will check, and maybe next time I will add it as an extra package to my presentation.
Would make sense. So Dimitri, we're going to check that and let you know afterwards. Thank you very much for your attention. Thank you, Aldo, again for the presentation. And I hope we see all of you again on the next 2 sessions. We are nearly done, but not yet. So stay in the next sessions. See you.
Bye-bye. Thank you.